Hey everybody, welcome back. Thanks for watching. If you're a fan of math, if you're a fan of trigonometry, calculus, linear algebra, proofs, you're going to want to subscribe to the channel. We've got a lot of cool stuff headed your way. Stay tuned. And with that said, we've got two neat little trig identities today. The first one's a quick one, and the second one is one that had me stumped for a little bit, and I want to give you a little peek behind the curtain. Now, typically I don't show the process of solving from scratch. You see the end result in the presentation of the problem. Just like for a musician, you wouldn't want to typically see their practice sessions, you want to see the performance. But I thought there was something sort of interesting that was happening in the solving process, and I wanted to share that with you, and you'll see that again during the second problem. For our problems today, we're going to need the following tools. First, we're going to need the double angle formula for sine, and that's sine of 2 theta equals 2 sine of theta times the cosine of theta, and we're going to use this result exactly in this way. For number 2, we're going to need the cosine of a double angle formula. So cosine of 2 theta is equal to 2 times cosine squared of theta minus 1. And similarly to this, we're going to use this result in this way. Now for number 3, we've got that classic Pythagorean identity. So tangent squared of alpha plus 1 is equal to the secant squared of alpha. For number 4, we've got the difference of perfect squares. And for number 5, if r is non-zero, then this product of reciprocals is equal to 1. Also, I want to give you a heads up. You're going to see these trig identities used in my next video. So in my next video, I'm going to be solving this integral in 3 different ways. Okay, so with that said, let's go ahead and check out the first problem. So our first trig identity looks like this. We've got the sine of theta over 1 plus the cosine of theta equals the tangent of theta over 2. And our strategy is to work with the left and see if we can arrive at the right side. Okay, so starting with the left side, we've got the sine of theta over 1 plus the cosine of theta. And we're going to use the double angle formula that I just mentioned for sine and cosine. Let's do that now. So sine of theta, that's exactly 2 times the sine of theta over 2 times the cosine of theta over 2. And then downstairs in the denominator, we've got 1 plus 2 cosine squared of theta over 2 minus 1. Now those will cancel, and we're going to have something nice. So this one sort of solves itself nice and quickly. Now from here, you're going to notice that a factor of cosine are going to cancel from the top and the bottom. The 2's will also cancel. So after I do that, I'm left with the following. I've got sine of theta over 2 over the cosine of theta over 2, which of course we know is tangent of theta over 2. So that proves our first result. And as I mentioned before, the next one is quite special. Here comes the peek behind the curtain. What was I sort of thinking as I solved this one? So for our next problem, we want to take a look at this. So we've got secant of theta plus tangent of theta plus 1 over secant of theta minus tangent of theta plus 1 is equal to secant of theta plus tangent of theta. Now, for a bit, I was a little stumped. I was playing with various variations of sine and cosine, and I probably could have arrived at it given sufficient patience or not running into some sort of bump in the maze. But what I thought of was the following. So I thought of the Pythagorean identity because we've got combinations of tangent and secant. And so I thought, okay, if I subtract tangent from both sides, I get the following. So this is behind the curtain. And so I said, okay, I've got the difference of perfect squares. That seems pretty nice. So if I factor that, it looks like I've got secant of alpha plus, well, tangent of alpha times the conjugate, right? Secant of alpha minus tangent of alpha. That's equal to 1. Well, that means that these are reciprocals. So if I think in this way, this will give me a strategy for solving this, right? So this means, again, so these are reciprocals. So I've got some situation like this, r times 1 over r equals 1. Okay, so what does that mean? Well, look at the form of what we have here. So this is r, because that's r, plus 1, over, this is the reciprocal 1 over r, plus 1. And then if I multiply the top and the bottom by r, I'm going to leave the top as is. Now downstairs, it looks like I get 1 plus r. And that's kind of nice because these will cancel and that leaves me with r. But r is exactly the result that that I'm aiming for. I mean, essentially I've solved the problem if you think about it in this way, but I'll just go through with all the details here. So that told me if I want to solve my problem, if I want to go from here to here, then I'm going to multiply the top and the bottom by r, which we said was exactly this, and exactly this situation will happen. Okay, so let's go for it. So we'll take this, and we're going to multiply the top and the bottom by r. Now this is r. So that's secant of theta plus tangent of theta. And see if you spot exactly this happening, but here. Okay, so let's take a look. So because of what I had here, I'm not going to multiply the numerators out, right? I kept it factored because this happened. But downstairs, the denominator, so I'm multiplying r times 1 over r. And if you think about it, if I multiply, so think about multiplying like this. So if I multiply like this, that's secant squared of theta minus tangent squared of theta. That's exactly 1. Not surprising because these are reciprocals. So that seems nice. And then I'll have this 1 times this. So I'll have secant of theta plus tangent of theta downstairs after I distribute. So let's see that in action. Okay, so downstairs, that's 1. And then multiplying here, there's secant of theta plus tangent of theta. See how nice that is? Again, it's exactly this happening. And I'm left with what I wanted. Okay, so I hope you found that sort of peek behind the curtain helpful and useful. Usually I don't show that. You just see, going from point A to point Z. But I wanted to share that with you. I thought that was actually maybe more interesting than just giving the problem. So what was the thought process behind it? With that said, stay tuned because, again, in the next video, we've got that cool integral of secant shown 3 different ways, and you're going to see this arrive in, I believe, the 3rd way. So check that out.